All right, so part two in the cylindrical shell method. Yesterday we introduced the cylindrical shell method, and we found that it's really a good choice when you're trying to find solids of revolution that are revolved around a vertical axis, because you don't have to rearrange your functions in terms of x, the x equals, y something, and then you don't have to kind of work sideways there, and it was nice and smooth for a lot of types of questions. Well, we're going to continue with that today, part two. And the question is the shell method ever used when the area is revolved around the x-axis, or is it just for a revolution around the y? Well, as I mentioned before, it's very nice to revolve this around the y-axis, right? You have cylinders that are upright, and the wraparound parts include the radius that is x and the height that is really f of x, right? Or the difference between two f of x. But this is the orientation when we're revolving around vertical. So horizontal, okay, is very similar, except things are just flipped around. So we're going to work on that today. So let's say we have, let's say our graphs are this and this again, maybe, and okay, and we're going to rotate this around a horizontal axis, like the x-axis there. And so what's going to happen is our cylindrical shells are going to be, the radius is this, and the wraparound part is going to be, they're going to be sideways now. Okay, so we're going to have these kind of shells looking like this, and so on. And then the shells are going to get shorter and wider and that sort of thing. Okay. Okay, so it's going to be the difference between the functions this way. Now, the cylindrical shell rotating this way, the cylinders, that's when you have dy, and you have, you don't have functions in terms of x, you have functions in terms of y, and the limits of integration on the integral are y. So some students don't like that. It kind of feels icky when you learn about integrals that have x, everything dx, which I get. But all you have to do is you're going to flip it around. So we're going to think of everything the exact same way, except we're going to flip everything around. It's going to be y instead of x, more or less. So let's take a look at number 9. And again, you can find the link to these questions on MrMathWell.com there, on the website. So here we go. Right here, you can click to these to this document, which looks kind of like this here. And these are the questions. So we're going to do number 9. You guys worked on some of these yesterday. Number 9 is where we're going to rotate this around the other way. So use the method of cylindrical shells to find the volume of the solid obtained by rotating the region bounded by the given curves about the x-axis. Sketch the region and a typical shell. So I've got a picture of the sketch here for you from the answer key sort of thing. So we'll work with this, and we'll maybe build our integral using this information and this diagram here. So we do have the function where x is isolated, and you do have to isolate for x when you're rotating it about like the x-axis or a horizontal axis. So we're going to solve for x for our function, solve for x, okay, if we need to, and this is already done for us here. And so x equals 0 is the y-axis, so that's a boundary. Y equals 1, here's y equals 1 on our diagram, somewhere around there, and y equals x equals 0, y equals 1, and y equals 2. Y equals 1 and y equals 2. Okay, so I can't really see where this is, just one such. So it looks like it'll probably be something like, maybe from here to here. Okay, so this might be 1, this might be 2. That's not on this diagram. So we're going to look for, this area revolved around, the axis here. So it kind of looks something like this, I guess. That's just one such cylinder that they have represented there on the inside. Okay, so it's going to be wrapped around space like this. I'll make it as messy as I can. Okay, so look good. Get it? So let's see what we need to do here. So we're going to have the volume is going to be, and again, remember 2 pi RH. right? So we're going to have 2 pi and then integral. Now, we mentioned that the thickness of the cylindrical shell is sort of that thickness of the wall is going to be our differential. So that's going to be in the y direction. So that's going to be dy. Okay, everything's going to be dy. So that means that this has to be in terms of y. The limits of integration have to be in terms of y. All of this is in terms of y now. Okay, they all have to be consistent. Okay, good. All right. So if we're going to go from y equals 1 to 2 here, then it looks like that might have to be our limits of integration. So again, the radius is going to go from kind of 1 towards 2. So this is going to be 1 and 2 here. Okay. And then I will sort of get rid of this so I can see this a bit clearly. But this is our x equals 1 plus y squared function. And so we've got r is going to be our y value. It's going to be exact same as the y value. It starts at 1, well, okay, and then it goes to 2. Okay, that's fine, wherever 2 was. So our r is going to be y. Awesome. Just like it was x for the other ones. The rotation of symmetry is just the x equals 0 line, right? So the radius is the same as the whatever the y values are. And then our height is going to be the height from the y-axis to the function, which if you've got this in terms of x in terms of y, then it's just the function itself. 1 plus y squared. There's no, lower function that we're squishing this area between, right? It's not like it's this area between two functions, so we don't have to subtract anything. It's just the straight value of this function. But everything is kind of sideways now. Everything's tipped over from yesterday. All right. All right. So this is an easy integral to work with. So let's just rewrite this 1 to 2. This is going to be y plus y cubed, I guess, dy. And I can go ahead and evaluate this integral. This is going to be 1/2 y squared, right? And this is going to be 1/4 y to the 4th. And that's going to be evaluated from 1 to 2. So the volume is 2 squared is 4. 4 over 2 is 2. Plus 2 to the 4 is 16 over 4 is 4. So 2 plus 4 minus 1 squared is 1. So that's 1/2 plus 1/4. So we're going to subtract those two things. So v equals 2 pi. That's going to be 6 minus 1/4. So that's going to be 5 3/4. However you want to think about that. That's 23 over 4. I guess. Minus. No, my bad. So this is minus the sum of these two. So that's minus 3/4. So that's 5 1/4. So 21 over 4. So 2 pi times 21 over 4. The volume will be 42 over 4 pi. Now that reduces to 21 over 2. 21 over 2 pi. Something like that. Double check some things. All right, so that is correct. Let's try another one. Number 11 here. So we have y equals x cubed. Oops, just gonna make some space. And if you want to make a little sketch here, that might be a good idea. You don't have to, but I think it's kind of nice to visualize that. So y equals x cubed from, so this is going to look like this. We got y equals 8, so that's up here somewhere. Y equals 8, and x equals 0. So I guess we're taking this and we're revolving it around the x-axis. I guess that's how that question was set up. Yeah, all the curves about the x-axis. Okay, sketch the region and the typical shell. So it does ask you to sketch the region. There's the region. The shell that we're going to be rotating around space is going to be sideways, so I'll draw one just in the middle. and it's going to go from there to there. That's your typical shell. So it is sideways, so v is 2 pi integral. It's going to be dy. All right. The r value, since we're rotating it just right from x equals 0, the r value looks like it's just going to be y. And the height is going to be the value of the function going from the y-axis, which means that I have to write this in terms of x equals something. So I do have to switch this around, right? I have to solve for x here. So I take the cube root of both sides, and this is going to be x equals cube root of y. Okay, x equals the cube root of y. You guys okay with that? So then, again, the height is just going to be that function, not plus or minus anything. So cube root of y right there. Now we'll want to simplify this integrand. We also might want to consider writing this as a 1/3 as an exponent, I guess, right? Why would that be advantageous? Because why? Anybody? What's your hint? So how do I simplify this? Yeah, same base, add exponents. Very good. Okay, oh, we didn't do limits. Limits are going to go from, we said 0, so 2, 0 to 8, looks like, right? 0 to 8. So it's going to be y to the 1 1/3 or 4/3, I guess you could say. All right, why don't you take a minute and see if you can complete this on your own from here now. Try and do that manually without a calculator, see how you do with that. Okay, so there's your answer for 11. Wow, that's loud. Thank you. Turn that off, please. Okay, now this type of question here, I want to let you think about this one for a bit. This asks, from a different perspective, each integral represents a volume of a solid. Describe what that solid looks like. So we just kind of got finished talking about the cylinder, right? If it's upright, like this, the cylinder is upright, then this is dx. The limits of integration are x in the x direction. The height is a function, y in terms of x. If you flip it over, it's the other way around. Right? You've got limits of integration are y, you've got the thickness of the outer shell is in a dy direction, and then the height is sideways, so that means x equals something something y. So it's a function, okay? So this one is going to be, let's talk some of these through. This one right here is in the dx direction, right? So the volume of a solid, which way is it going to be revolving? Around what type of axis, vertical or horizontal? It's going to be around a vertical axis, okay? So vertical axis of rotation. All right. The 2 pi is just part of the wraparound. That can come out. We have x to the 5th. So what does that represent? Okay, we got x to the 5th. Now remember, we have to have r and h in here. R and h, right? So if 2 pi is gone out front, then we're focused on x to the 5th. So what could you say about that? What's usually the radius? What's usually the radius in these ones? It's usually just x, right? So the radius maybe is x, right? And so what would the function be? The function might be, yeah, x to the 4th. X to the 4th function. Because when you multiply those together, that's what you get, right? Yes?
Could the radius ever be like x squared or something?
Could the radius ever be x squared? Well, no. It's going to be some terms of x. It's going to be the x values, plus something if the axis of rotation is beyond just the y-axis maybe, or it's going to be minus that if it's shorter than the x, or it's going to be a number minus x. Remember we did that yesterday too? But no, it won't be x squared. The function could be x squared, of course, but the radius will probably just be x plus something or minus something, or something minus or plus x, whatever. Okay, does that look good? You guys okay with that one? Okay, this one is going to be a rotated it's going to be rotated vertically, right? Or this way, because it's a dy. So, oh, we didn't do the 0 and 3, I guess. It's going to be taken from 0 to 3, whatever this is. So, maybe something like this, I don't know, x to the 4th. I guess it's x to the 4th is pretty flat, just x to the 4th. So, okay. So it's going to be kind of like this and rotated vertical axis like that. Okay. Now this one is going to be the other way around. So we're going to have y looks like our radius, right? And then we have 1 over 1 plus y squared is going to be our function. You don't have to draw it, I don't think. Just describe it. This is the function. Radius is y. So it's going to be rotated around the x-axis, perhaps. And we're going to go from y values of 0 to 2. Okay. So I don't know what this graph looks like just offhand, but it's going to be rotated vertically. I have some kind of graph. 0 to 2. X equals 1 over y, 1 plus y squared. That's going to be your function. All right, now here, see, here's where, for number 31, here's the radius right here. This is the radius, so look at that. So now we're going from, it's dy, so we're going from 0 to 1, and we're rotating around the axis of, looks like 3. So 3 minus y. Remember, the rotation of axis is sort of beyond. The rotation of axis is over here, and we have this solid of 1 minus y squared. Y squared plus 1. So what's that? Like something like this? I don't know. Okay. So this is your function. X equals 1 minus y squared. And you're rotating it in space this way about the horizontal line, y equals 3, looks like. And these are cylindrical shells here. Oh, that's bad drawing, sorry. Yes, hand up in the air over there.
Yeah, if you multiply the...
So if that was expanded, then it would be just a jumble of terms. It would be just a polynomial of terms sort of thing. And you wouldn't be able to tell what's the function and what's the radius. So they show it like this so that you can see, hey, this looks like the radius here with just the y, and then this must be the function. So they're just kind of helping you out to identify those parts.
Could that create 2 different cylinders? Like, because technically that's equal to the expanded version.
Oh yeah, when you're solving for this, you multiply that through and get individual terms and then take the integral and all that. That's how you solve it. But I'm just saying, if you were given this in the form of the expanded form, you wouldn't be able to pick out which is the y and which is the function. So they just read it in this factored form so you can see each. Make sense? Yeah. Okay, so there's the questions that pertain to the vertical revolution around a horizontal line there. 9 to 14, 21 to 26, 29 to 32. Work on those. I'll be primarily focused on the even questions from you.